Hi, my name is Brooke Myers, and today I'm going to be presenting on the DCl Lab. First, I'm going to start by giving a brief overview of the main goals of this experiment and my hypotheses. Then I'm going to discuss the theory and methods used in this experiment. I will then go over the results of my experiment and finally make conclusions based on the results and the takeaways from the lab. Infrared spectroscopy is a useful tool for understanding the structure of small molecules. A main goal of this experiment was to understand the theory behind IR spectroscopy. This was achieved by preparing proper samples of HCl and DCl, which we ran in the IR spectrometer. From this, we produced viable spectrum. The spectrum allowed us to determine the molecular constants of HCl and DCl. From these determined values, the goal was to understand how the mass of atoms impacts bond properties. My first hypothesis is that DCl will have a smaller rotational constant than HCl because DCl has a larger mass than HCl. This results in DCl having a larger moment of inertia, which is the reduced mass of the molecule times the radius squared. The moment of inertia is inversely proportional to the rotational constant, and therefore the larger the moment of inertia, the smaller the rotational constant. My second hypothesis is that H2O will be observed at lower wavelengths compared to DCl. Because HCl has a smaller reduced mass, which is inversely proportional to the vibrational frequency, this will result in HCl being observed at higher wave numbers, which is the inverse of wavelengths. This is our full IR spectra for our HCl-DCl sample that we ran in class. On the spectra, we were able to label the overtone and fundamental transitions, which are explained in further slides. And in addition to that, we were able to differentiate between the DCl and HCl peaks. In our lab manual, we were given values for HCl and DCl, which this confirmed our hypothesis too that HCl would be at higher wave numbers than DCl, and this is because wave number is directly proportional to energy, because wave number is the inverse of wavelength, and wavelength and energy are inversely proportional. So this also explains why HCl is observed at the higher wave number than DCl for both overtone and fundamental transitions. Looking at a bond as a harmonic oscillator models this equation, and this states that it can stretch and compress with no limit, which we know isn't possible, so we have to quantize vibrational energy, and this is represented by this equation, where VE is equal to the harmonic frequency. In order to account for anharmonicity, which we know that the bond will have, we use the realistic Morse potential, which is represented here. And this takes into account the molecular dissociation at large values of x, and x is the displacement, so either stretching or compressing from when the bond is at equilibrium where it's not stressed or compressed at all. And dE is the potential energy relative to when the bond isn't stretched or compressed. And A is a constant that determines the curvature of the potential. And in the Morse potential, we see that as energy increases, the energy spacing decreases. And from this equation, we see that VE is the harmonic frequency and VEXE is the anharmonic constant. Looking at rotational and vibrational motion together, when we want to see the transitions between different states, we have to look at both the energy transition from V0 to V1, which would be the fundamental transition, which is seen over here, and also the energy transition from V0 to V2, which is shown here as the overtone transition. And the overtone is necessary because it allows us to calculate the harmonic frequency and the anharmonicity constant, which are necessary to determine the bond energy. And we know that the first overtone occurs at half the wavelength, which is inversely proportional to wave number, so double the wave number of the fundamental transition. We can group the transitions into two classes. One class has decreasing rotational number, which is seen here in the P branch. So this is where delta J, which is the quantum number, is -1, also seen here. And these are listed at lower energy levels. And then the other group is when the rotational quantum number is increasing, which is seen over here in the R branch and here. And these are listed at higher energy levels. Okay, I want to briefly go over the molecular constants we're solving for. So V sub 0 is the wave number for the first transition, whether it be V0 to V1 or V0 to V2. BE is the rotational constant. DO is the bond energy. D is the centrifugal distortion constant, which is only significant at higher energy transitions. Re is the internuclear separation at equilibrium, so when the bond is neither being stretched or compressed. K is the vibrational force constant. V sub E x sub E is the anharmicity constant. V sub E is the harmonic frequency. dE is the potential energy when the bond is not being stretched or compressed. And A sub B is the rotational vibrational coupling constant. While running a background scan on the IR spectrometer, we added 1.5 grams of NaCl to this 25 milliliter round bottom flask. After that was added, we ensured everything was set up correctly with clamps and grease, and all of the valves were in the proper orientation. Once everything was secure, we opened the valve and added 4 milliliters of protonated sulfuric acid to the round bottom flask. This was done very slowly. Once all of the acid was added and there was time for it to transfer to the IR tube, we took the IR tube to the IR spectrometer and ran our sample for the HCl DCl in the IR spectrometer, which then produced a spectra that we exported to Excel for further analysis. So from our large spectra that we saw at the beginning of the presentation, we were able to zoom in. This is the DCl fundamental spectrum with all of the wave numbers listed for each of the peaks and their transitions. In order to calculate the molecular constants, we had to plot the transition number versus the maximum wave number for each transition for the R and P branch in this polynomial regression form, which gave us these equations for the corresponding branches. The equation for the P branch for the fundamental transition is listed here, and this is the equation we got from our polynomial line of best fit. So you can see how these correspond to each other. So from this, we are able to plug in for these terms and solve for the constants. The R branch fundamental equation is slightly different, so we used that equation compared to our polynomial line of best fit for the R branch and then repeated this process of finding the constants with the different equation. And then we did the same thing for the HCl fundamental data. So we had our zoomed in spectra with the labeled maximum wave numbers and our transitions for R and P branch. We were able to graph them and get a polynomial line of best fit for each of them and then use those to solve for the molecular constants for that as well. We then did the same thing for DCl overtone that we did for DCl and HCl fundamental. However, these equations were slightly different, but it was the same idea of using the polynomial line of best fit values that corresponded to these terms in the R branch and P branch equations to solve for the fundamental constants for overtone as well. Using the same equations we did for the DCl overtone, we did the same thing for the HCl overtone, following the same steps as the fundamental, just using those different equations again. From this point in the calculations forward, we used averages, so these two tables just summarize for fundamental and overtone. Here we can see that the rotational constant for HCl is greater than the rotational constant for DCl for both fundamental and overtone, which this accepts hypothesis 1 that the rotational constant of DCl will be less than that of HCl. So using the averages, we were able to determine V sub E, X sub E, and V sub E. So we were given two equations for the fundamental and for the overtone transitions, and then we used a system of equations to solve for V sub E, X sub E, which I did over here for DCl. And then once you knew V sub E, X sub E, you were able to plug in and solve for VE. And this V sub O A is for the 0 to 1 transition, and the 0 to B is for 0 to 2 transition. So this would be your overtone, and this would be your fundamental. Using the harmonic frequency and the anharmonicity constant, we were able to solve for dE, which is the potential energy when the bond isn't being stretched or compressed, and dO, which is the bond energy. And I did a sample calculation for DCl. Okay, so we were also able to calculate RE, which is the bond length at equilibrium, so with no compressing or stretching. And I did a sample calculation for DCl. over here, and then the force constant, which is the vibrational force constant. I also did a sample calculation for that for DCl as well. And then I just wanted to point out these intensity equations. So the intensity can also be modeled using Boltzmann distribution, which would give theoretical values, but both Boltzmann's distribution and these equations explain the curvature of the P and R branches. So the curvature comes from the combination of this degeneracy term and also this exponential term. So that is present in our experimental data and our theoretical data. And this is just a final summary of those molecular constants that we were just solving for after we had the averages. From the results, I was able to accept both my hypotheses. The experimental results allowed for proper analysis in order to determine the molecular constants for both HCl and DCl. One limitation the data calculations may have is that the overtone was much weaker than the fundamental, which reflected in the p-branch polynomial regression having larger errors than seen in the other spectras, which would have affected some of my calculations. We could compare our intensity transitions to a theoretical spectra, which we could produce using Boltzmann's distribution. This will allow us to determine the percent error of the calculations since we didn't necessarily have anything to compare them to in our lab. Thank you for listening.